Hello, welcome to Crystal Core Skills. In this video, we are going to look at what is called Pythagoras Theorem. So we are going to look at what Pythagoras Theorem is and how to prove Pythagoras Theorem, how to show that Pythagoras Theorem is actually true. So the first thing we are going to look at is actually let us look at what is this Pythagoras theorem. Pythagoras is actually he was a Greek mathematician who brought up this theorem called Pythagoras theorem. We're not going to go into the history, but he was a great philosopher who defined Pythagoras theorem, and he came up with a theorem known as Pythagoras theorem, which states that the square of the longest side, of a right angled triangle is equal to the sum of the square of the two remaining sides. So the longest side of the right angled triangle obviously is called hypotenuse, and the shortest side is the opposite, and then the medium size or the base one is called adjacent. So this theorem says that the square of that hypotenuse is equal to the sum of the square of the two sides. Let's try to state it mathematically. Hypotenuse square is equal to the opposite square plus adjacent square. So that is what Pythagoras' theorem says. So let us just try to use the initials for these to actually make sense, to make it short for us, like to create a kind of like short form for us to understand. So let's say this is h equal to o square plus a square, which means that h is our hypotenuse, o is the opposite, and a is the adjacent. So this is what Pythagoras' theorem is all about. It is the square of the hypotenuse, which is equal to the sum of the square of the opposite and the adjacent. So that is, my friend, what a Pythagoras theorem is. Now, how true is this? Yeah, how true is it? Now we are going to use what is called similarity, congruence, and geometric means or ratio. We are going to use these three concepts to verify that Pythagoras' theorem is actually correct. So how do we do that? What we need to do is to come up with, because when we're talking of this hypotenuse, opposite, adjacent, we are obviously referring to right angle triangle. So right angle triangle gives us the best way to understand this. For example, you can have a right angle triangle like this, so that the hypotenuse is there, hypotenuse, which is our h, and then the opposite side, which is our o, and the adjacent is here, which is our a, so that we can have that right angle there. So this is a right angle triangle ABC. So we are going to use this right angle triangle by applying the concept of similarity, congruence, and geometric means to prove that the concept of Pythagoras theorem is actually true, or to derive that formula, so that we know how to get to that formula and what we need to get to that formula. And what we need obviously are these similarity, congruence, and geometric means. And then how to get there? We are going to apply this in order to derive that formula by using obviously the giant right angle triangle. So let us see how to go about this. So we are proving Pythagoras' theorem, which says that, let's say Pythagoras theorem, which says that opposite square plus adjacent square equals to hypotenuse square. So this is the theorem of Pythagoras, the Greek philosopher who came with this theory. How true is it? So we're going to use our right angle triangle. Let's say this is our right angle triangle, obviously with side A, B, C, and we know that one is our hypotenuse. Our hypotenuse is here is H, which is our hypotenuse. Hypotenuse is the overall distance between between B and C is H, and we know that this is our opposite, which is O, is the distance between A and B. This is our A, and then we know that that one is our C, which is adjacent, which is A. So this is the distance between A and C. So we are going to apply what is called an altitude to split these triangles, this triangle into many triangles, because we want to use similarity and congruency, which requires at least two triangles for us to be certain that we are doing some comparison analysis here. So we are going to, an altitude is a line that divide or intersect intersect line segment at a right angle. So you can imagine an altitude like going high, something like you have horizontal line, and then you want to see how high that something can go. If you when you go and watch my video on the lines and different types of lines, you will find a lot of information about altitudes. So it always intersect a horizontal segment at the right angle. So let us assume that this horizontal segment is that long side of the right angle triangle, so it will intersect at that point. Now let us give this point D, so that we can have the distance between BD as our X, and then between D and C as our Y. And as you know, the overall distance is our hypotenuse, which is our small h there. So let's see how we can now use this information to prove the Pythagoras theorem. So the first thing we are going to do is to extract the different triangles that we have there and compare them with the big one. So let us start by extracting the bigger triangle, which is, let's say, triangle BAC is equal to this triangle here. This is the big triangle. Obviously we have three triangles there already. Let's say triangle 1, triangle 2, triangle 3 is the big one. So the big triangle is triangle 3, because that bit there, that one is our triangle 1, and that one there is our triangle 2. So we have three triangles in total, and the third one is the big one. So we're going to compare the small ones with the big ones and then come up with the formula of Pythagoras theorem. Now let's say we have our right angle there, ABC, with our hypotenuse there and opposite there and our adjacent there, so that we can have a perfect right angle with all the sides. And also we have the second triangle, which is triangle ADB, ADC, so that we can have our triangle there like that, That one is A. It intersect at D, so our D is there, and then AD, we have our this will be the short the altitude, the apex is A, and then we have B, we have C there, so that A, yeah, our C is there and our A is there, such that the longest side of our small triangle, this is triangle 3 obviously, and this is triangle 1, so the longest side of this triangle will become AC, which is our, it was initially adjacent, but here is going to be our hypotenuse, and DC is our Y, obviously, DC is our Y, and we don't have any AD there. So clearly from here, you can see that these triangles, they are all right angle triangle and they are similar to one another, but we need to find out what condition of similarity do they fall under. And when you see this, we have side here, we have side there, and they meet at this vertex here, which can create some sort of angle, and that one as well, the side there, and they meet at that angle, and they are all meeting at the same angle, so that we can have this condition known as side angle side, side angle side. So they're similar, these two triangles are similar, because if you apply side angle side, we find that all of them possess this condition for similarity and congruency. So we know that they're similar and we know that they're congruent to one another. So we can just say that triangle BAC is congruent or similar and congruent to triangle ADC. It's because of that condition there. Now the second thing to do here is, so we have used similarity. The second thing to do is to use geometric means to come up with the ratios, to see how one is a rescale version of another. So how can we do that? Now we are going to apply geometric ratio by looking at the hypotenuse of each of the triangle, and these are the sides which are common to each of them. So the ratio of the big triangle to the sides of the ratio of the sides of the big triangle, we are going to pretend that is equal to the ratio of the side of the longest side, which is the hypotenuse, and the adjacent of the smaller triangle. So we are going to assume that these triangles are the same, and as we have verified using similarity and congruence, we concluded that they are in fact similar and congruent to one another, which is another way of saying that they're the same. So this allows us to apply geometric ratio. So let's say we have used similarity here and congruent, and now we are going to use what is known as geometric ratio, geometric mean or ratio. So when we apply this, that one is done already. Now we are in the second one. So let's see, we are going to compare them now. So this is the shortest side in here, so we're going to put it on top. AC, the segment AC, divided by the segment BC of the bigger triangle is equal to the segment, this is the shortest one here, segment DC, divided by the segment AC of the smaller triangle. So when you do this, you will get, let us extract the real value. So AC is A, and BC is H. BC, this is our C. Remember, don't mistake it with that A, because that A, we just used it to demonstrate the side angle side constraint for similarity and congruency. So we have our A over H, adjacent divided by hypotenuse for the bigger triangle, is equal or similar, if you like, is similar to the adjacent of that smaller triangle, which is DC, which is y, divided by the hypotenuse of that smaller triangle, which is our A. Now from here, you need to do what is called cross multiplication. So you can cross multiply here, and you get something like a square, because a times a is a square, which gives us y times x, y times h, which is y h. So this, my friend, is our first equation. You can just name it like equation number 1. So the second thing we are going to do here, is to use the same triangle, which is triangle BAC, and let's draw it out. It's the same triangle 3ABC, hypotenuse HOA. Remember, this is our bigger triangle. This time we are going to compare it with triangle number 2. So let's have that triangle number 2 here, which is our is D there is here, D is here, and then our B is going to be at the top there, because this is the shortest the shortest side of triangle in that of that smaller triangle, which is our X, and we have obviously the remaining part, which is our A now is here. Now as you can see, we have triangle we have triangle BDA. Let me write it there, BDA. So we have our two triangles now well set, but we need all the sides. So we know side X from there, and we have the opposite side there, which is BA. So BA is our O extracted from that big triangle. So O is hypotenuse from here, but it was an opposite side for the bigger triangle. But when we extract that part of the smaller triangle, we get the O to be our hypotenuse from here. So now we can see, my friend, we can see that we have two perfect triangles now. This is triangle 2. Now we are going to do comparison analysis to see the similarity and congruency aspect of these two triangles. Now as we can see, the first triangle, which is the bigger triangle, has all the sides, but our second triangle, which is the smallest triangle there, has only two sides, which is the hypotenuse and opposite. So those are the sides we are going to use in order to assess their similarity and congruency. Now we can see the opposite side is there and the hypotenuse side is there. The opposite side is X on the other one, and the hypotenuse side is there. So we have two sides, and then those two sides actually meet. You see, they met there at the apex at B. So from here, my friend, we meet the same condition as because the side angle condition is met. Side angle. So this condition for similarity and congruency is met. Therefore, we can say that triangle BAC is in fact similar and congruent to triangle BDA. So our similarity aspect is met. So they are similar and congruent to one another. Now the second thing is to use the same geometric means or ratio to see the scale version of one triangle on the other. Obviously this triangle is the smaller one, so how small is it? So we're going to compare this using what is called geometric ratio. So from here we are going to use the hypotenuse and the opposite, hypotenuse and the opposite for each of the triangle. And notice that for the first one we use hypotenuse and adjacent, hypotenuse and adjacent, because we had no opposite side there, and here we have no adjacent. So we can now use our geometric mean here. So let's see the longest side and the smallest side. So obviously you put the smallest one on top. So segment BA divided by BC of the bigger triangle equals to segment BD over segment BA of the smaller triangle, which implies that we have our O there divided by BC, which is our H, is equal to, we have our X there, which is BD divided by BA, which is our O. So doing the same cross multiplication, my friend, we get O squared equals to XH. So we can call this one our equation number 2. Now, the third thing we are going to do here is to add these two equations. So add 1 plus 2. So adding a two equation gives us a square plus O square equals YH plus XH. You can call it equation number 3, but we are going to simplify this one now so that we can, so that we can come with a square plus O square equals, this one you can factorize it out so that you can have Y plus X, and then our H will be outside there. And notice from the bigger triangle that H is our hypotenuse, and when you take X and Y, when you add the distance, these two distance, you get our hypotenuse. So X plus Y is actually equal to H. So when we bring that H here, instead of putting X and Y, we are going to put H there, so that we have a squared plus O squared is equal to H times that H there, and this will give us a square plus O square equal to H square. You can write this one in any order, like O square plus A square equal to H square, which gives us the same answer. So my friend, as you can see, we have come up with perfect Pythagoras theorem here, and this, my friend, is how to prove Pythagoras theorem by using similarity, congruency, and geometric mean. As you can see, this one is exactly the same as that one there, my friend. So thank you for viewing, and I hope this video has been informative, and please subscribe, share it with your friends, as well as give me your comments, because your comments are really important for me to learn from my mistakes, as well as share ideas with you as we're doing here. So thank you for viewing, and I hope this video has been informative. Thank you.